Device.
Hello, everybody. My name is Kevin Kawchak. I'm the founder and CEO of ChemicalQDevice. Have more people filing in. So this week we're going to talk about quantum machine learning, quantum GANs, and then this quantum federated learning. So of course, with any technology, it takes a while to build. And it's interesting to see kind of like the pieces coming together, with quantum and then, in a somewhat an established field. So I shared this before, but basically I'm going to be going over these three main sections. So federated learning, generative adversarial networks, and then you also have, some background as well. And, we get more people coming in here. So basically this first article is really quite something. It's Nature Biomedical Engineering. It's got, not only this quantum machine learning, but this federated learning, and then the other topic that we'll be going over as well. As you can see, so the name of it's called Shifting Machine Learning for Healthcare from Development to Deployment and from Models to Data, Making it a Reality. So for those of you that don't know, federated learning is somewhat of a common thing. Apple, Google, others have used it for different purposes, and it's taking a little while to, fully incorporate into medical. It's basically you're forming your models. Your patient data never leaves the site, when you're doing your hospital, as iterative training is going up in the cloud with other hospitals as well. So this is basically what they say. And all along the way, I'm going to point out things that, are likely going to see quantum incorporation in the form of quantum internet, quantum sensing, quantum computing. Now, if you look on the left-hand side of this diagram, it says the current limitations, need for storage and a data pipeline for training, capabilities for data normalization, computing power, and secure communications. So as you can see, and as with any technology, a lot of these aren't going to likely be pure quantum, as was discussed on this panel before. And it's just, basically a gradual incorporation with quantum technologies as is needed. So this is basically a really good chart. So on the top, you want to look at centralized learning versus cross-silo federated learning versus cross-device federated learning. Now, centralized learning is the most common, but it's only a single hospital, so that their data sets are somewhat restrictive. With the cross-silo and a cross-device FL, this is where you're doing your patient data, models on site, and then you're sending them up to the cloud, and then this iterative model keeps on forming. So it's important to realize that none is perfect. Obviously, there's been a somewhat of a push for this federated learning in recent years. Now, you'll see this, and Google's very into this. They have this thing called digital twins or Google for Patients. And it was used during COVID-19 for chest CT lesion segmenter. So this has to do with medical imaging. And then what they found is basically 99% of centralized training performance, even if you have imbalanced data sets or relatively few samples per institution. And the hard part is basically getting all of the standards correct, like all of the computing at each facility to be the same, as it's trained on the site, and then as it goes to the cloud. And it's an iterative process. So you start a new round, number one at the top, current copy of the model is sent to each location where the training data is stored. And then you have number two model, each copy of the model is then trained and updated using the data at each location, keeping the actual patient data on site. And then the models return. And number three on the bottom, updated models are sent from each location back to central server where they aggregate into a global model. And you see with number four, redistribution, the results from all these hospitals are sent back to the individual sites. So you have subsequent, rounds of training follow. So the cross-device federated learning, this is basically I'll show you a picture here too, is Apple's used it for voice recognition for Siri. Google's used it for Android, mobile devices, and FedHealth, it's this IEEE article as well. And it's basically, to be continuous, the amount of data that's going to be growing is exponential in healthcare. Number one, because it always is, but number two, especially with IoT and wearables, you're going to have people wearing all these sensors, just more and more data. So that's hence the need for more and more of this. So here's a good illustration of where the industry's been. So Google, April 2017, improved query suggestions for Android. Number two, FedHealth, July 2020, builds relatively personalized models for transfer learning. Transfer learning has popped up as, it's basically keeping a lot of what you've learned before and just changing something like fine tuning. Then Apple with voice recognition for Siri. So it's somewhat accepted. So the longest or the part of it is getting it into healthcare, because these are hospitals, with all different types of people and all different types of hospitals. So high degree of coordination. You need normalization and standardization protocols, all these types of things to protect that patient data. It's really important as you're sending a model that's trained based off a bunch of patient data, but not necessarily sending it to the server. And of course, there's a lot of responsibility for the individual institutions. And then, while you're doing this, you can't actually directly inspect data during development. And then, so Google's got its, hands in with a lot of this. Is federated analytics using GANs, create synthetic data. And this is for population level summary statistics. And then it's currently unclear if tools for cross-device versus cross-silo are interchangeable. So all this work that's been done with Google and Apple, can it be used for hospitals? Those are the silos in that case. And then, many of the software is still proprietary. So open source frameworks are intended for use in research. So to conclude, or to continue with this, is basically each participating healthcare institution acquires necessary infrastructure for encryption. So there's going to be pushes out there, as there's a push for cybersecurity with quantum technologies, post-quantum cryptography, these types of things. And there's going to be a push as well, with quantum, with federated learning, with the other technology I'm going to go over as well. And then, these, CPU, GPU, QPU systems could potentially help as well, boost up capabilities. And I'll get into GANs a little bit later, but there's many hands in both federated learning and GANs. It's really quite interesting. And most hospitals just are used to dealing with data centrally, as opposed to, in this federated learning system. So there are some privacy risks, and it's basically, it's inherent when you are dealing with patient data. It can reveal sensitive information, and it is the same thing with anything data leakage, and you could infer back to this original data. Basically, it's saying if the machine learning model, memorizes the actual patient data, but there's a number of things in place and going to be to help with that. And then you have, the solutions, as they say, differential privacy and the selective parameter sharing and sparse vector technique. Now, some of these, in the sake of privacy, you're going to give up some in the sake of performance. So this next article, so this is a quantum federated learning neuroimaging article, and it's basically, it uses variational quantum algorithms for this decentralized data, and it's using TensorFlow quantum, and it also, the algorithm demonstrates model accuracy, from decentralized data, and it's suitable for more near-term processors. They say likely the NISQ era that we're in, NISQ. Now, it has its own, it's the same kind of thing as far as like iteration, mainly focused on centralized data training before. So it's that whole push to use QFL. And hopefully a lot of these things will see quantum technologies just because they make sense in certain cases. And that, a lot of people think of just quantum technologies as quantum computing. It's either noisy or it's not, when in reality, there's a wide range of hybridness. So in this case, they use blind quantum computing to avoid third-party theft. And then they also want to incorporate transfer learning into future studies. So here's one of the models. So you can see if you were to flip this, as opposed to the first image that was shown, it's very similar in its layout. So the local data is where you have patient data. Local models are trained from that local data. And then each of these models, local models goes back and forth to this, to the cloud. And then it's updated and iterated as it goes. And just this is the way of doing it in the quantum realm with VQAs. So basically, the proposed QFL algorithm had improved in performance, and they're saying in the variational task of decentralized data. Now, there's other techniques of VQTN, which is tensor network, COA, which is optimization algorithm, and VQE, which is eigensolver 2, which is also having a play in a lot of this as well. Now, in this third article, this is also a QFL for neuroimaging, and then in specific, they're saying that this is from 21. It's a bigger paper, and they're saying it's the first fully quantum federated learning framework using existing wireless infrastructure. Now, keep in mind, they didn't actually transfer qubits. It's just other types of quantum technologies. And then, they're say they also use Google's, TensorFlow federated, and then this TensorFlow quantum in this case for effectiveness. Now, you'll see this a lot, and they say basically if there's issues with error, as there is with quantum computers today, is use a quantum convolutional neural network architecture. And in this case, it's 8 qubits in the QFL setup, 3 pairs of quantum convolutional pooling layers, 64 learnable parameters for a suitable QCNN. So that's oftentimes they say, okay, if it meets these requirements, QCNN. And then, so here's what it looks like. So this is the author's diagram here. So the key with this is basically it's hybrid. They say it's fully quantum in some respects, and it's a QCNN model, but it's the same kind of thing. You have your individual clients or hospitals at the bottom, and then so you're training based off patient data, and then so it's communicated back to the server, this 5G infrastructure. They say hopefully this could be for 6G as well. Now, as with most papers, if you're not doing simulation, you're doing these experiments on low number qubits, just the inherency between barren plateaus, and then local minima, and then complexities, other complexities as well. And then, so the challenge with this is large scale, purely quantum QML models. And then I'll show you again, as far as like this Los Alamos National Laboratory paper, is the same kind of thing. It's, the more quantum you are, the higher chance you'll get quantum advantage. And I'm talking about quantum sensing, quantum algorithms, quantum memory, and quantum computing. So this allows for training QML models inside, like I said before, the 6G and efficient optimization algorithms. Now, both of these curves are based on their QFL network. So in one case, the red dotted is centralized, like how most hospitals are today. And then they're both QFL. The top one is federated. So this is where you do your training, and then you're not concerned about the patient data anymore as it sends to the cloud, or it's already trained and it's not an issue basically. So that was interesting to see. And then basically with this paper is that the authors proposed this novel framework. As I said, no qubits were transmitted. And it's interesting because you'll see in other countries, in our country, we're at like 100 kilometers terrestrially, transmitting qubits, sometimes both classical and quantum at the same time with Argonne National Lab and Fermilab. And then, another thing driving all these things is the DCQNet in Washington, D.C., as they say, we will have a national quantum internet. So it's just a matter of time. And then obviously using TensorFlow quantum and TensorFlow federated. And then these results basically validate the behavior of the proposed QFL framework using federated averaging algorithm. So again, these papers are detailed, which is a good thing. Now, I don't know who hasn't heard from GANs, but GANs is a huge thing, and there's so much across the internet as far as just Fortune 500 companies and doing whiteboard presentations, and that's where I learned a fair amount of this. And there's things called GAN Go. So this is basically you have an adversarial network where have real data and simulated data. The simulated data comes from random noise. And then over the course of training, your image gets better over the course of time. So this is the whole, these are just regular GANs. So everything wants to move into healthcare. It's, just the issue with a lot of this is how can you control, regulation is, these images that were produced partly from classical and quantum, how can you actually tell, like what's a good metric basically? The GANs have been used by big companies in the past. So you have a generator and a discriminator, and I'll show you a diagram upcoming as well. So the whole big aim with it is to implicitly learn data distribution from a set of samples to further generate new samples drawn from learned distribution. Now, the GANs can suffer from training instability, low image diversity, and quality, which could hamper deployment in clinical practice. And then, of course, with the regulatory hurdles there. Now, I can't stress the amount of research that's being done, and this paper, I believe this one's actually for brain tumors. So there's so many different things you can do with GANs. So in case number one, it's taking this CT image that was acquired in real life, and then you're translating that into an MRI image. So you see this progression, and it's basically through training these networks with the, these adversarial networks. Now, number two, it's also for denoising. And then number three, for image classification. And number four, for predicting disease progression. So these are longitudinal studies. So there's a whole host of things, and it's just a matter of, when it really makes it in the healthcare world as far as, it's basically regulated, and you could make sense of these generated images from real images and from non-real images. So the whole goal is to get Nash equilibrium. So that's hard to do because these networks are working against each other, and it can be unstable, sensitive to hyperparameters. Now, in the original GAN that was people were working with, it had these issues. So the solution is just to make more GANs. And here it is. So you have changes to the loss function with WGAN and so on, conditional GANs, and then changes to model architecture. And just as with this, and a subsequent paper too, is, I'll kind of show you a diagram of how this lines up. And basically, in the real world, how it is today is most training is still done centrally, and this is only if you have large, diverse data sets. And it's just a matter. So if they say if you have 90%, or if you have 10% of the training is real images and 90% is generated, from artificial, but it goes through this feedback loop, that's actually pretty good results. And then for healthcare, it's just proving to people that this is, in the long term, going to be a lot better off. So you could do certain things with my paint program or anybody's on your computer. You can take an image and flip it and all this kinds of stuff, but it's not the same kind of effect that you get from using this type of adversarial network. So here it is. So 3 cases. Convolutional neural network for classification was trained on both synthetically and traditionally augmented data, and it improved by 10%. So that's one case. Now, another case, models trained on synthetic data and fine-tuned with 10% real data resulted in similar performance to models trained on real data sets augmented with synthetic data. And then this third one, using synthetic data generated from GANs to train image segmentation model, was achieved 95% of the accuracy of the same model trained on real data. Now, in image translation, it's basically like I said, it's taking a CT image and converting it to an to an MRI. It's really quite remarkable. And you need some level of real images in there. And with this, and it's people have experimented with, it's called GAN Go, where you have like you're guessing which image is real and which is artificial. There's another one. It's basically saying each of these people are real, but they're generated from artificial images, based on other real data. So it's really quite remarkable. And for clinical use, mostly it's been used to augment balanced data sets and patient privacies. And then, as you can see, so on the third bullet point there, it can be used for dangerous and rare clinical scenarios. For instance, incorrect surgery, modeling spectrum of brain tumors, or exploring progression. So this would be longitudinal studies of neurodegenerative diseases. So obviously with ChemicalQDevice, it's always about making new, better images using quantum technologies. And then what this is saying is a lot of the industry is also, on top of getting your good, better images, using training with these adversarial networks too. And, a lot of these, so you have complexities due to the regulatory process. And basically, your performance testing is hampered by lack of efficient and robust metrics. So this is the whole thing, is like at the end of it, how do you evaluate this, compare and control? And the encouraging thing is all these types of GANs are used today in our smartphones, search engines, self-driving vehicles. Now, this GAN article, so this is the one in specific for brain tumor, and it's basically super GANs. So you take 3 different GAN models and create this aggregation. Now, keep in mind, they get the images of each 3, and then they're taking the best 2. So I'll show that a little bit later. So it's used, you have the brain tumor. This is Brot's common data set. And then it's tested by this SSIM scores. Now, this is where it's at right here. So without getting caught up, but basically you have this generator in the blue, and then you have the discriminator in the pink. Now, what helps me the most when I look at this, besides, you have random noise that actually goes into the generator. So it's like within any, learned network, the image gets better over time, is that, after the pink, it says real or fake. So it gets to the point a lot of times where it can't tell. And that's where, you get your accuracy loss, all that kind of stuff. And then on the right here, you get back propagation as well. But it's really kind of an interesting thing because, like I said, you're always going to need the real images. But, the issue in the real world is there's a lack of high quality data across the board. So these GANs are thought to, if they can prove it in certain ways, if the real images are good enough and you're only using 10% of that, and then 90% of your generated images as it gets better are very comparable, that it may start to work its way more and more into healthcare. And this is for the paper. So this is their specific one. So this is how I said these, samples, images, are the real ones. And then so the DCGAN 1 and 2 and the WGAN, you generate these 3 different images. And then based on this SSIM score, the 2 of them are aggregated. And then afterwards, it's style transfer. So here's the metrics. So the 2 they mostly refer, well, they didn't really refer to the KL divergence as well, but the SSIM and then the SD, they refer to the most when comparing it, its performance. Occasionally the PSNR as well. Now, here's a table, and basically, so this is for brain tumors, so glioma, meningioma, and pituitary, where they have it bolded and aggregate in the table. You'll see sometimes they'll bold the SSIM, PSNR, and the SD, and it's basically saying, compared to least squares GAN or information maximizing GAN, it's tending to do better, this aggregated method. And the reason why they use these is so DC GAN is for better quality images and more stability, And then WGAN is for model stability during training and a loss function that correlates with the quality of generated images. Now, keep in mind, most of the previous work, and this is where they're saying this paper kind of stood out, is that it's just to, their other work using a single discriminator aggregator doesn't stack up as well, and they may get higher correlation, which in this case, correlation is bad. You don't want, two images that look the same. And then, so here's the quantum. So here's quantum GAN. So quantum generative adversarial networks. This is December 2021. And then they used it with 20 qubit superconducting qubits and, with a quantum gradient algorithm. And then everything's quantum, right? So I'll show you the diagram with this as well. Is basically this QGAN runs automatically for rounds to achieve this Nash equilibrium. So you have these two networks that are against each other, and you want them in equilibrium. So this is it. So this should look familiar to those who program in quantum. So basically, you have A is the logic behind it. It's similar to the classical. And then B is the superconducting processor. So it's using these 5 qubits. And then C is the interesting part, because this is the, Hadamard gates. You have staff notation, but this is actually, because this paper in specific, it has both generator and discriminator that are quantum. And, a lot of times that's just achieving that in the quantum realm. That's, for today in late 2022, this is really something else. So you see, methods do not require accurate implementations of specific quantum logics. And then QGAN, so there's other problems in quantum that it could be used to solve, and this is called quantum many-body problem, optimal control, and self-guided quantum tomography. And then keeping in mind, with all these bigger circuits, you get barren plateaus. So just with more qubits, the ability to have wide plateaus just inherently gets shorter or narrower. And then, it's basically saying you can use deep quantum neural networks and the corresponding gradient backward propagation algorithm as well. So here's Article 6. So this is another QGAN. Now, this is November 2019, and it's kind of more fundamental in its approach, or it's an earlier paper. So it's basically about loading. So they're saying for efficient loading, instead of getting 2 to the n number of gates, and we've seen this in other areas of quantum too, it's only poly times n, which is non-exponential. It's polynomial, which is in the favor of using quantum in this case. And then they used 2 different ones. They used for hardware, quantum simulator, and a 20 qubit quantum processor as well. So this is the current article I'm talking about, Article 4 on the actually, sorry, these are flipped. It's actually 5 and 6, but the one on the top is the paper I'm describing right now, and it's just the quantum generator. And the one on the bottom is it has the generator, discriminator, and it's really more built up on the quantum aspect with GAN. So for those that haven't seen, there's a number of awesome resources out there. So this is pulled from a paper in electronics, and basically this is more just the fundamentals of quantum computing, gates, transformations, and so on. And then in this one, if you haven't caught it in previous episodes, this is the big table of quantum artificial intelligence. So it goes through all of these CC, CQ, QC, QQ. Most of them are QC supervised. And then likewise in this, and it ranged from 1994 all the way to 2016, but that's a good paper there. Now in this Article 8, I've shared this number of times, it's challenges and opportunities in quantum machine learning. Now, a lot of these things, so quantum federated learning, and any other type of, GANs, they're type of machine learning. So my guess is a lot of times people won't refer to things as hybrids, they'll just call them quantum whatever, because they have some aspect of quantum in them, even though, it's just in the early phases of a lot of this with application. And then, so the key is basically to use as much quantum as possible. Exponential advantage in quantum comes from, if you have these quantum mechanical processes. And then this one's specific because I've covered quantum image processing before, which is a different area, but that seems more time complexity. And then this is basically saying your best chance of getting exponential quantum advantage will be from sample complexity, such as brains, using quantum sensor, memory, and all parts quantum computer. And then they say likely hidden parameter extraction. And then this one, so this is from that same paper, the Lannel paper, is basically many signs are pointing to QML for a lot of this. They say quantum chemistry, material science, learning, coding, QML subsets, and so on. And then this is kind of like the whole paper that so this is based on the Google Quantum Supremacy October 2019 Sycamore, 53 qubit gate-based superconducting qubit paper, quantum supremacy, quantum advantage. Well, it's taken some hits since then. And then so this year, and actually it was December 2019 was the archive paper, but in Science of this year, they came out with this paper, and basically what they're finding is in this weird quantum world where you can have quantum memory and entanglement. And actually, instead of just measuring something right away, as you would do classically, you're holding on to it and you're entangling it. So in the bottom left, it describes that QML saves a copy of the qubit state, entangles it with the next copy, learning about quantum state more quickly. So this is actually like a huge thing. And it's contrary to kind of belief, but this is quantum sensing, quantum memory, quantum computing to use a faulty Sycamore noisy quantum processor to get so the noise is no longer the primary component. And then here's their data that goes along. Now keep in mind they're comparing it to conventional. It would have been cool to see compared to the original quantum supremacy. But for them to publish again, this is with Caltech and Harvard as well. These results likely mean a good amount. Now, the research that ChemicalQDevice will be going into is basically to get better images. So quantum sensing, quantum imaging, QIP or QIP or quantum image processing, quantum machine learning on the bottom as well. And then optimizing quantum circuits, QGANs for training, collaborating, and especially as this goes with healthcare for this federated learning with quantum as well, to work with other institutions, hospitals, of getting better models. To be a part of that would be like an honor. So it doesn't have to be all of these. It's just these are what are available. And then in the previous decks at the bottom there too, where it says prospective ChemicalQDevice, is that there's rationale between using quantum sensors. There's rationale between using third-party QML with quantum, third-party quantum sensors, quantum memory, quantum hardware, that kind of stuff too. And I've shared this before. This is the circuit optimization option slide. So this is basically optimizing circuits on the startup's own to go into a QML setup, that is more favorable to today's noisy environment on the right there. This is a very popular, so this is medical image processing by analog devices. So the important keys to take away is you have image formation for option 1, and then you have image computing for option number 2. And then say there's for detection for option 1 is basically quantum sensing, reconstruction, figure quantum algorithms, MIT has some. And then for option 2, it's more, CPU, GPU, QPU with enhancement visualization. So here's the sensing option. I'm really impressed by this QPSD paper. It was used for noise reduction on audio waves, but it can also be done for vector magnetometry. And anytime they're saying distortion-free, the article title is called Quantum Assisted Distortion-Free Audio Signal Sensing. And the bottom articles, especially the one in the lower left, they did a phenomenal job. Millimeter resolution. This is magnetic information from a rat's heart instead of today's centimeter, because it's biocompatible and it can be placed closer. So not every quantum sensor is the best. You know, sometimes with the diamond sensors is just they're diamond, they're inert. They can be placed closer, and a lot of times that has advantage even over if it's not as sensitive as like a squid, you know, like superconducting. And then here's another one. So this is a QML option. So this is incorporating quantum sensing, quantum algorithm, quantum computing, and moving forward. And then this is a whole thing too. So quantum machine learning, neuroimaging, basically the best of the best with QML, you know, what's available in quantum sensing and computing, and then algorithms, internet, cybersecurity moving forward too. So it's interesting as far as like, as I see other posts, they say like a quantum medical director would be another position out in the field. But as many of us know, it's just, you know, likely going to be a lot of hybrids. So whether the name quantum gets applied to everything, or if we keep quantum AI or QML, or if we call it AQ, AI quantum, we'll likely be seeing it. And then also here, compound annual growth rate for AI and medical imaging is close to 46%. And that's greater than the quantum computing market. Also with that, medical imaging, neurology is the principal component of that. So quantum computing market, you'll see a bunch of CAGRs out there, but this is 33%. And of course, the guiding light for a lot of this has been NSF's 2023 Practical Quantum Computer. Here's previous decks, and then here's basically a summary of what's in each deck. If you're just looking, you know, to learn more about specific things, I'll post this deck. And here's the mission statement: to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and/or resolution, leading to advanced prediction and neuroradiology for Alzheimer's disease. And the goal for 2023 is to develop QML, quantum machine learning, neuroimaging improvements utilizing medical research collaborations. Here's additional information about Alzheimer's. So here's the an accepted revised mechanism of it all. And so you see the interplay between amyloid beta plaques and then tau, and how it affects different parts of neurons, microglia, and astrocytes, and so on. And then a good site to keep up with this is Neuroscience News. There's been a lot of interesting news with this. And it's not on here, but basically, is the brain a quantum computer? And the hardest part to fathom with that is they call it a hot and wet environment to do quantum entanglement. But it was interesting. It's making news. And I'm also seeing other parts of that on LinkedIn. And then here's some Alzheimer's disease organizations to support. And that's the end of the presentation. So I'm going to stop this. And it's good to see a number of people, returning people, new people as well. So why don't we, as far as this, so Riska, Pratik, if you have anything, you can unmute or you can come on. And then if not, so Azure or I'm not sure what part of that is your name, but BKHADM. So either of you can come on, ask questions. So chat. Okay.
Oh, sorry. Can you hear me now?
Yeah, go ahead.
Yeah, the BKHADM is me. I think I'm using a different computer, so it's slightly different thing. The information you gave, or the paper you talked about the 1 millimeter resolution versus the normal 1 centimeter, have they shown an exact sample and get the better resolution, or the preparation of sample, for instance, it should be thinner or not? I mean, they can really put a big mouse, or they have to slice part of it to get that 1 millimeter resolution?
Yeah, so this is actually in vivo, and then the comparison is against squids, which is, yeah. So it's the thing with the diamond quantum sensors is they're really close. They're biocompatible. They're talking about actually using them for internalization in cells. And they compared against this other quantum sensor called OPM, optically pumped magnetometry. Now, OPM, the current generation of the sensor, technically has better signal to noise ratio. However, that specific detector couldn't be placed as close, we're talking about standoff distance, as the diamond quantum sensor. So yeah, it's a really good paper just because, I mean, heart is 100 times magnetic information as brain. It's just, yeah, I think that's typically where they start with a lot of these. And, you know, they compared it to 3 or 4 other different rats. They have a bunch of supplementary material, and they provide a bunch of information as far as if them or if you would want to make a better diamond quantum sensor, you know, what would you look for or how would you do it? So it's a Nature paper. But yeah, that seems like, I mean, I like the QPSD paper with the noise reduction. They say it can be applied to vector magnetometry, which is what we're talking about. And, you know, it's basically ChemicalQDevice or others, you know, could take, you know, technologies from each of these, like MIT has an all frequency, you know, quantum sensor. And then there's a reduction in readout noise. There's one that used machine learning to get better results as well. And so, yeah, unfortunately, Ryan, I had to bite the bullet and pay for the Nature subscription. They just put the abstract, so it's $30 a month. So I just cancel something else to get it. I would suggest anybody to definitely review that paper. And you know, it's not technical. It's more like a review and then where things are headed with QML, but somewhat of a standard that we have for QML. And the Google, so if you can't get that, if you still want something else, the Google, Caltech, Harvard is very interesting. Now the science paper is not available. You have to pay for that, but the archive from 2019 is available, but I had a hard time gathering the important points, and I got my most from the Google blog from June of this year.
I see. So, I mean, 10 times improving resolution is something huge. I mean, if their system is, I mean, system size is reasonable, they should have already been like they put it in how they say commercialized it. So
Yeah,
I don't know if it's just a one-time measurement or has a huge like room size laser and all those things or
yeah, so its path is towards miniaturization. It's nanodiamonds. It's not big. It's not like the Hope diamond. So actually, in this case, it's carbon diamond, and then you omit carbon, put in nitrogen, and then you have a vacancy next to that nitrogen atom. And then when it's fluorescence. So you're shining green light and you're emitting red at that vacancy, and that vacancy has quantum spin, like up, 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 down, or down, up, you know, the 3 combinations. So the one that's up, down is the one that creates hyperpolarization. And then so you're reading the red light that's coming off from due to fluorescence. And, you know, they have them for EV batteries. They have them for, they did use a brain sample where it was in vitro. So it's just a really fine slice and it's really close, you know, because it can. So yeah, the inherent benefit so far has been, well, number one, it's potential, because they're saying, you know, you could put it in 2009, basically, NIST said this, that on the tip of a rod, and then have it pick up magnetic information like a little mini MRI instead of a big MRI. So yeah, that's the whole goal with this, is just right now, in order to control the quantum effect, you need a microwave generator, or, you know, to keep the spins up, you know, down, up. And yeah, everything, they want to use it both ends, you know, laparoscopically or endoscopically, you know, and that's the whole thing, is to keep getting it smaller. So
the whole package is not small enough right now. That's why it's not industrialized yet.
Yeah, I'm not sure as far as, because if you can shine light through fiber optics and do microwave, you know, generation, you know, not right there, but somewhere else. But yeah, I think the whole goal, in my mind, would be to eliminate as many of these other atomic force microscopy, other these surrounding things to,
I
and
see.
every, you know, quantum sensor application is different. But yeah, it's been mentioned, and it's there's a quantum sensors. It's quantum.gov, and it's called Quantum Sensors for Fruition. And then they have this big, you know, paper on quantum sensors, and then a really nice feature as far as, you know, it's been used in microscopes and all this kind of cool stuff.
Nice. Thank you very much.
Yeah, Tim?
Yes, when getting my PhD in physics, I was doing computational modeling for the process of the protein aggregation that forms the amyloid beta fibrils for Alzheimer's disease. But, you know, and at the time, what they were saying was they couldn't see that process in vivo, like, you know, actually do some kind of scan of an alive person. So how well does this would this technology be able to do to get, like, you know, information about the formation of an amyloid fibril in the brain of like a live person?
Well, I'm seeing some interesting stuff on LinkedIn the past couple of weeks where it's trying to think, it's on the molecular scale, right? And it's not specifically that amyloid beta fibril, but you know, it's just, if you were to, because I've done other talks on other types of things as far as like fluorescence and super resolution that breaks through the diffraction limit and all this kind of stuff. And then I think, and we've talked about this before with SEM and TEM, as far as being the most fine-tuned, seeing down to nanometer, you know. Yeah, so doing it in vivo. So, okay, so we've talked about, so a lot of these sensors are placed on the brain, and I believe they're a lot more sensitive than your MRIs and your PET scan and even your CT, right? It's just, you know, their standoff distance is really close. But if you're talking about the internal of the brain, you would likely need that MRI or PET scan or, you know, these types of things, CT, in order to see these types of things. But their sensitivity in relationship with other, you know, super resolution microscopy and other types of quantum sensors, even squids, or potentially squids, but there's OPMs and diamond. So I'm not sure exactly as far as the exact technique to see that in a person. And then we have invasive, right? So these actually sit onto the surface of the brain, and I think that may be the best chance. It's just not, as far as I know, I think it's just the surface. It's not on the inside, but it could provide enormous insight to what your query is.
Okay.
And then anybody else we haven't heard from? Ron, do you have anything? And then if not, anybody else that we haven't heard from? So Pratik or Rizka? And then if not, Azer. Yeah, and I just want to give a brief kind of overview here. Is basically there's been, I did this thing is that we're into a new era in healthcare for quantum. Now, this is due to a number of big news articles. In specific, last week, they announced that Cleveland Clinic and IBM are making their first quantum computer on Cleveland Clinic's campus, so the first quantum computer in healthcare. And then you had President Obama, you know, supporting the technology at the quantum, you know, Chicago Quantum Exchange, these students that are learning about the technology. And you had President Biden in the past couple of weeks as well go to IBM. They're announcing $20 billion, not just for quantum, other high-tech technologies as well. And there's a picture of President Biden and then the IBM, I think his name's Arvind, CEO standing behind a quantum computer, and then there's an American flag in the backdrop. So a lot of those things just help kind of cement as far as the level of confidence a startup could have, or anybody else interested in the technology, as far as like, okay, if we have two presidents in this past month that are basically associating with this technology a lot more. You have President Biden basically saying that this could be the new quantum computing hub in New York for IBM. So a lot of those things kind of like build up. And I guess the biggest kind of beacon that I've had is National Science Foundation's 2023 Practical Quantum Computer. And that hasn't gone away. But that's a huge thing to go from where we are with our IBM or say Xanadu or Quantinium or IonQ, that we have something a lot more tangible. And there's been more trips, other investors going to, kind of like people well known, going to IBM's, this is within the past week, facility. And other people have said it too, is basically, really excited about this type of quantum technologies for 2023. And I'd be interested, number one, how other people in this discussion have gotten into quantum technologies. Number two, how basically you reflect on all that news, especially in healthcare. And then there's Sandbox AQ with Mount Sinai Hospital in New York. There's Fermilab and NYU Langone basically saying we're going to make a quantum computer and other quantum technologies to make MRI better. So, I'm not sure if you'll get that sensitivity boost like a 10x or 100x, but, it's basically you'll start to see that wherever it makes sense to have quantum, it'll start to incorporate. And then anybody else we haven't heard from? Farhad, I saw you just came on. There's a question in a chat. So it says, please advise where I can read about more quantum sensors. So I have a number of things. So in this deck, I have 20 links that, so this is the quantum.gov. This is, basically the top, these are early applications so far in quantum sensing. So I would check out this deck because it's got, if you look under quantum sensors on some of the later slides, it's the outline kind of looking thing, is that has enormous benefit in my mind. And then Ron, did you have something?
I just had a question about one of the slides you were showing where they were talking about using 20 qubits in it's part of one of the GAN prototypes. Was the 20 qubits actually being directed towards the neural image itself, or was it, did it say anything about where in the neural network it was being used?
Well, I think there was two articles. I think article number 6, and that's actually one of the earlier quantum GANs. So this is where they just got the generator, and I compared it to the generator and discriminator. And they actually took it and compared, and as far as their charts, I just wasn't quite sure because the terms and all that kind of stuff, but they compared it to their running with quantum simulation, and it didn't look favorable. So, and of course, that's back in 2019, and it's a specific, that's a specific IBM quantum computer, right? So this is 2 years, or it's basically the year of quantum supremacy, 2019. So yeah, as far as the quantum hardware that was used, I think maybe only 1 or 2 of them where a lot of times they'll use like a 20 qubit and only have 8 or 6 that they're actually running off of that. But I would say,
like if you have 20 qubits and if you were actually applying that to like a convolution layer since you're doing neural imaging, you're getting some sort of dimensional image data. It kind of maps out to being you can do processing on a 1K by 1K single bit depth image, and I'm just wondering how useful that is.
yeah, and a lot of these.
I'm not sure that's why I'm asking if that's what it was used for. If it was just the 20 bits or the, whatever subset of the bits were used, again, more for a optimization step.
Yeah, and I don't think it got anywhere close to doing, simulation of the brain, or it's not anything like that. Now, I think the one that you're talking about, if you could remember, if it was like 2019, this was actually a financial paper with Monte Carlo and, cost returns. It was one of the early kind of like buzzy, quantum technology papers right after quantum supremacy. And it's a thorough paper, but I think the moral of the story is just like, they're all noisy. And like they say, I think if they get above this 8 or 20 qubits that, with real quantum hardware, I haven't seen anything really productive. Even there was a recent paper, there's a IBM and Amgen paper, and they did quantum kernels for rheumatoid arthritis data. And they said they used both quantum hardware, quantum simulator, and then the result is basically, they said it was as good, if not better than classical results. And a lot of it's like going through motions, especially with the quantum hardware, getting awesome results, or not getting awesome results.
Yeah. Well, I mean, it's undoubtedly technology that is really waiting on quantum volume to actually do some really serious work, I think.
Yeah, so for those that don't know, so quantum volume is number of qubits over error. So you want, for your numerator, high qubits, and your denominator, low error. And on this topic, quantinium, they keep doubling it. I think they're up to 8,000. And I think the 4,000 quantum volume, that was only on like 10 or 20 qubits, and basically keeping the error as low as they can. So a lot of times, I think most experts or most programmers would want a quantum computer that's lower in lower in qubits, but a lot lower in error. And even INQ has an approach with 32 qubits next year. And we're due for an IBM 400 qubit. So kind of like the telltale on that will basically be how much less error does this have over the 127? So, because it says it can do like dynamic circuits. So,
yeah, I guess if they were going to push this towards image processing, there probably are some techniques like sliding convolutions where they don't necessarily, especially if you're going to use the quantum for the lower layers or the initial layers, if you want to look at it that way, of a machine learning stack. It's easy for those layers to do localized work on an image where you're not working on the whole image, you're just looking at pieces of it at a time. But so much that could probably be done there, even if they're not using it for imaging, they're just using it to accelerate, or optimizing the loading of initial parameters and stuff like that. There's a lot that could be done with that.
yeah, I appreciate that. So I asked a question. I asked, what area of Alzheimer's disease will benefit most from quantum machine learning? So I got some pretty interesting answers. So there's a gentleman, his name's Francisco. He said all. And then Alex said prediction. So that's kind of what I'm thinking. This is basically if you have better images, you can project better into the future because you can see more what's going on. Now, Powell, who has been a previous guest, speaker, he says diagnosing. Sebastian said prediction. And then I think, so it's Faye said detection. And then Sumyan Deep said drug discovery. So I guess a lot of these things is like, when I was hosting a lot and having speakers on it, I kind of thought like, okay, where could this wind up? And I was like, well, it needs an application. So I really have to focus on healthcare, right? It's more resistant than other industries to recession, these types of things too. And that's where, lots of these experiments and presentations to go with it. But in any computing technology, and this isn't just, you know, quantum, this is the original, is it needs an application. And that's when I really told myself I really have to get into primary literature and see what's really going on. And somebody asked about that Lanol paper. I think Ron asked about it. Those are the types of papers you really want to read, because it says basically, you know, I mean, it's obvious now, but to get the highest quantum advantage, use the most quantum in your sensing and memory and computing. And then some things weren't clear as far as, like, you know, time complexity, not as important as sample complexity. So sample complexity basically means what you're, you know, what you're looking at should be a lot more complex as opposed to the time aspect to it. So yeah, all those types of things, you know, and it's just piecing puzzles together, and it's less about your specific research and it's more about what's been done, because there's a fair amount that's been done not only in quantum hardware, but quantum machine learning. And then we're seeing quantum federated learning, these kind of early things. But we had, you know, this a QGAN, you know, with both discriminator and the other generator as well. You know, some steps, right? And a lot of this data from these early quantum papers aren't awesome. Like even the most recent that I can think of really good healthcare one, the IBM and Amgen, it, you know, its conclusions were basically as good or better than classical, and nothing close to exponential results. So, but yeah, the bottleneck is with hardware, quantum computers with a lot of these things, because quantum sensors are, MRI and laser are technically quantum sensors, and that's been decades, because they operate on the principles of quantum mechanics. But with quantum computer, you know, if you have good coherence, high number of qubits, these types of things, it seems like in watching the news and, you know, the presidents involved, the current president and the previous president, and then the IBM Cleveland Clinic, you know, quantum healthcare computer, you just got to put these things together, and you just, you know, you kind of wait, but at that same time, you need to study applications. It's the same thing with studying GANs. So with this GANs, if you go to this website, I think it's all of these people are fake or something like that, and they actually use other technologies such as, I think, GPUs to generate a really good image of somebody that isn't even real. And this is that whole thing of maybe 10% of the data is real, and, you know, the rest of it is from random noise coming in. And then, did you have something, Farhad? But yeah, it's like the more you know, with a lot of this basically, and is, you know, it's all in the primary literature. I highly suggest getting you know, subscriptions to some of the leading journals. They pay off as far as like knowing what you're talking about, because that's usually, like, at the end of the day, that's what matters, right? And then any other questions or comments? Anybody we haven't heard from? Go ahead, Ron.
Quickly, are you aware of anybody actually using or actually building diamond sensor scanners for human use? Is this still all in the laboratory stage where they're looking at mouse brains, and how far away do you think that is? And another question would be, is there anybody anywhere compiling this raw diamond sensor imaging for research purposes somewhere?
Okay. You know, I think back, there's an ACS nano paper, and I want to say it was last year, and that's where they say, like, internalization of cells, you know, these types of things, like really kind of microscopic. I don't think that would be nanoscopic, but just these really kind of in vivo studies. I don't see the harm in going from the rat heart to the human head or whatever you want to do, you know, because I don't know if you remember this, but basically the OPM the OPM quantum sensor has better signal to noise ratio, but than the diamond quantum sensor, but the diamond quantum sensor was placed a lot closer. So that's that standoff distance. So yeah, it's basically, that's the whole crux of it, is to do exactly what you're talking about, because it's bioinert. And I don't think that's the case for a lot of other sensors. And also it can measure not only magnetic, electric, but temperature, force, and I think strain. So it's, if not the most versatile. So it's basically wherever it is, measuring fluorescence effectively, right? Like the phenomenon is the sensor sits in this magnetic field or whatever, it's shining green light in, and they're measuring red. And as long as you can do that, and you might need some microwave generation, you know, to keep things in line. But as long as you can do that, that was my take on it, is basically that's where it's heading.
Yeah, so I mean, I can kind of envision that what might be coming down the line is, instead of sticking a patient in a massive MRI machine, they will maybe slap a helmet on you.
Yeah, I mean,
And that the helmet would be lined with all the sensors, and it would be, you know, non-invasive, safe, but good. I mean, it could be just contact, surface contact based.
yeah.
But so my question is anybody getting close to a working piece of diagnostic equipment
That I'm not sure. It's
to
just
use on humans? Yeah.
like with any technology, because that was the '09 NIST article, and you know, they said that it was sounding like it wouldn't have taken what was that, 12 years, because that was '09 to 21. And last year they figured out the algorithm to better understand the red coming off the fluorescence. So I'm trying to think, but same thing for Ron, like in this or any of the previous decks, I've got 20 links on all those as far as
Sure.
quantum sensors, and it's in the quantum neuroimaging outline. And then I would just click through them, because some of them, like I think the first 4 are more general, and then they get more specific as far as you know, using ML with this nano diamond ensemble, then spin amplification to help with the readout noise, you know. So that's basically what I'd look for, you know, in my startup, is how I can combine these technologies, and learning things from like the rat's heart to the, you know, noise reduction, that kind of stuff.
I mean, are you working on an end-to-end solution, or I mean, it seems like there's opportunities at several steps in the process. That's what I was asking about.
Right.
Are there data sets available? I mean, I don't have the space to set up a a big or any sort of medical diagnostic equipment, but if the raw data is out there, you know, it's like sort of like crowdsourced science or whatever, or the minced challenges that got machine learning launched real quickly, where all these test databases are out there, and people can download them as like open source data, and run, you know, experiment with their algorithms and their not I mean there's a lot you can do with just machine learning, but
Yeah.
also now that the quantum algorithms are coming on, you know, not everybody's going to have access to that diagnostic hardware, but if the data is there, a lot of people could have a shot at coming up with the rendering and the diagnostic steps, for example.
Yeah, and I would say we're early application, because this is August, was the rat's heart millimeter resolution, and then the QPSD distortion-free audio sensing. And then in September, there was they used 2 diamond quantum sensors in an EV battery setup. So instead of getting 10% accuracy of the charge rate going down the road, somebody said closer to 1%. So that helps with range, you know, if you can better detect what's going on at that specific time. And there's temperature, I've been seeing sunlight, you know, diamond quantum sensors, but I would look for the big papers and then kind of chart that, because the one for the rat's heart, they provided so much insight as far as what they could make better. You know, sometimes the laboratories are in the works of already doing that. It's just not for that current paper, or they really understand the technology, and then, you know, the next round of funding or whatever, then they can do it. So, and then Tim, did you have anything?
No, nothing else.
Yeah, so okay, so just kind of like a recap here. So we talked about federated learning, quantum federated learning, GANs and QGANs. And I guess the moral of the story, the takeaway, is some of the papers are more advanced than others, and just because of the year as early as 2019, and then others, you know, last year or this year. And, you know, there's a lot to look forward to, because I once was told, even I'm a chemist by trade, is that everything in the future is going to be data, you know? So you really want to, no matter what field you're in, you really want to understand data. And this is like futuristic movies, that kind of stuff. You know, I have one in my mind, Ready Player One. But, you know, that kind of approach is basically lots of data, lots of machine learning. And then as a chemist, I was kind of concerned because I see these machine learning experiments outperforming the top chemists over, you know, the course of 20, 30 experiments or more. And then that's reason to really understand everything that's going on. So, but yeah, this has been episode 54. I appreciate everybody coming on. So a copy of this will be available on the channel. So it's ChemicalQDevice, the letter Q in the middle. And then I'll also post the deck. I appreciate all the feedback. You know, definitely hang in there, everybody, with quantum, with all the news going on, and especially the forecast for next year. So yeah, other than that, thanks again, everybody, for coming, and have a good rest of your night. Take care.